Let's talk a bit more about the geometrical representation of complex numbers and actually this connection with vectors. As we've seen, all complex numbers can be represented as vectors. Here's x plus iy, join it up to the origin, and I get a position vector. But of course, what we saw about vectors that is useful is we can move these things around. So I could slide that vector down there. Now, it still represents the same complex number, because as we saw with vectors, no matter where you put it, it's still the same vector. So I could slide it up there. It's still the same complex number that it's representing. So it doesn't matter where we put it, its length, or when we talk about complex numbers, modulus, and the angle it makes, the argument is consistent. Okay? And remember, if ever you want to work out what the actual, in this case complex number is, head minus tail, and I'll tell you the complex number it's representing. That therefore means the addition and subtraction is exactly the same as we saw with vectors. There's complex number z1, and there's complex number z2. If I want to add these complex numbers together, we create z1 plus z2. A little parallelogram we could create. z1 minus z2, well, the actual complex number is down here, but as we saw, we can slide them and it turns out to be the other diagonal, z1 minus z2. This brings up a nice little inequality, the triangular inequality. So we know in any triangle, one side will always be shorter than the sum of the other two sides. Shortest distance between any 2 points is a straight line. So in triangle ABC, well, I didn't actually label a triangle up there, but in any triangle ABC, AC would be less than or equal to AB plus BC. That now tells us a property about complex numbers then, because these three moduli represent the sides of a triangle. So therefore, the modulus of z1 plus z2 must always be less than or equal to the modulus of z1 plus the modulus of z2. In fact, I could rearrange that and express it in a different way. I could write it as AC minus AB is always less than or equal to BC. So the other part of that inequality, the modulus of z1 plus z2 will be bigger than z1 minus z2, but it'd have to be the absolute value of all that, because obviously one of these sides is going to be bigger than the other. You might end up with a negative number. When is it equal? Well, when all three lie on the same line. So you don't have a triangle, basically. Wow, very old question here from 1995. They gave us this little diagram, told us that P represents Z, Q represents W, thus the length of PQ is the modulus of Z minus W. Head minus tail. And basically there's the triangular inequality. That's what they want you to use. Show that. So how would I write it down? Well, I've just drawn in the third side there and said, well look, the length of OP would be the modulus of Z, OQ would be the modulus of W, PQ the modulus of Z minus W, and then all I've got to say is, well, by the triangular inequality, the modulus of Z minus W must be less than or equal to the sum of the other two sides, so mod Z plus mod W. They then ask you to construct another point representing Z plus W, and then what could be said about our quadrilateral? So we draw up our diagram, complete the parallelogram, the other diagonal is Z plus W, so there's R. What do we know about this quadrilateral? Well, it's a parallelogram, because we've created the parallelogram with our vectors. Okay, but then they ask this interesting question. Well, if those two are the same, so the mod of Z minus W and the mod of Z plus W, what could you say about W divided by Z? Now, using geometry, it comes out quite nicely, because they've told us this. If we go back to our picture, we've said it's a parallelogram, you'll remember. We know the diagonals in a rectangle are equal. So actually, our quadrilateral is a rectangle, not just a parallelogram. If it is a rectangle, then I can look at the arguments of those two things, because the vertex must be a right angle. So the argument of W minus the argument of Z must be, well, I'm using radians, pi on 2. But we saw when we play with arguments, subtraction is division. So the argument of W over Z, which is what we're interested in looking at, is equal to pi on 2. What does that tell me about W and Z? It must be purely imaginary. Because if you were to plot a number that has an argument of pi on 2, you would end up on the imaginary axis. So we have a purely imaginary number. So I didn't have to use any algebra there to get that out. Just using geometry, it comes out nice and neatly. Multiplication then. This is something we didn't actually look at in vectors. We looked at the scalar product or the dot product, but multiplication of two vectors together. We know this rule. The modulus of z1 times z2 is equal to mod z1 times mod z2. And when it comes to the arguments, we know that, well, when we multiply, we're actually adding the arguments. If I now put that into mod arg form, r cis theta 1 plus r2 cis theta 2, play around with that, we get r1 r2 cis theta 1 plus theta 2. So what is this telling me? Well, when we multiply z1 times z2, the vector z1 is going to be rotated anti-clockwise by the argument of z2, and their lengths will be multiplied together. And that will be our new vector. Here's a lovely little picture here. So what we're saying is if we multiply z1 by cis theta, in this case we've made the modulus just 1, that vector OA will simply rotate an angle of theta. The length's not going to change because I've said the modulus of the other one is 1. If we were to multiply by r cis theta, now the length would change accordingly. It would be multiplied by whatever that r is. And that brings up our very important one here, this rotation of 90 degrees, because we know the cos of pi on 2 plus I sine pi on 2 is I. So if we're going to rotate pi on 2 or 90 degrees, it's equivalent to multiplying by I. So in other words, IZ1, you'd get OA and you'd rotate it anti-clockwise 90 degrees. Very important. And just another little reminder there, vectors, remember, you want to work out what it is, head minus tail. So I've got this picture here. I haven't actually said it. That's a square. All I know is A and D. D is just sitting at 1 on the real number line. A is just some complex number, omega. How could I write B and C? Well, if I look at our vectors, to get C, well, the vector DC, I could get the vector DA and multiply it by I, because if that's a square, I'm rotating at 90 degrees. Okay, what is DC? Well, C is the point I'm looking for, so whatever that is, minus 1, and that will equal omega minus 1 times I. I'll make C the subject of all that, and there's my expression for C. It would be 1 minus I plus I times whatever omega was. So how can I get to B? Well, I could say from the point A, I'm going to add on this vector. I can slide it up. It's the same vector, the vector DC, which we just worked out. So if I add to the point W, C minus 1, which C we just worked out over there. Playing around with that, we've now got an expression for B. That's one way I could have got B. Another way I could have got it, I could have said, hey, from the point C, which we just worked out, I could slide the vector dA over and add that on, and that would get me to the point B. If I did it that way, and thank goodness we get the same. But there's another way we could have got B as well, because we know this is a square. So I could say, to get to B, I'm rotating the vector dA 45 degrees. So I know the diagonal in a square will bisect that vertex, half a 90, 45. But I also know that in that right angled triangle, the isosceles right angled triangle, the sides are in the ratio 1, 1, root 2. So the length of the diagonal would be root 2 times the length of the side. I could get the vector dA, which we know, and multiply it by root 2 cis pi on 4. Let's do that one. So dB, that's what I'm trying to find. Well, B minus 1. Root 2, I've written now in cos plus I sine, because I'm going to need to calculate that out. And dA, that's omega minus 1. It's B I'm interested in, so I slide that to the other side, and eventually, yet again, we get the same result. So there's more than one way of getting there. Just as we saw with vectors, when we're trying to find them, there were different ways of getting to the points. In the year 2000, they asked this one. It's a rectangle. And we're told the length of OC is twice the length of OA, and A is omega. What would C be? So how do we get to C with what we know? The only thing we know is A. All right. Well, I could rotate the vector OA. It's a rectangle. I know I'm rotating at 90 degrees. They've also told me the length is double. So that vector would double in size. In other words, I'm getting the vector OA and multiplying it by 2i. So let's sub in what we know. There's an expression for C, 2i times omega. What complex number corresponds to the point of intersection D, which is the diagonals OB and AC, that point of intersection? So OB and AC. Well, what do I know? I know in a rectangle, diagonals bisect each other. So I'm finding the midpoint of AC or the midpoint of OB. Either one would find it. But I don't know what B is, so it doesn't really make sense to play with the midpoint of OB. But I do now know what C is, and I know what A is. That makes more sense. So we'll find D as the midpoint of AC. Midpoint, well, remember A and C are points, so I'm just adding the two together, dividing by 2. So whatever A is, whatever C is, I'm going to divide that by 2. And we know both of those, and there's an expression for D. Half plus I times omega. Let's look at something a bit more recent. The 2022. We have a complex number. It satisfies that the modulus of z minus 4 on z is 2. They've given us a bit of a hint, although they have said you could do it another way if you want to. But usually with these sorts of questions, they're giving you a big hint. That's probably the best way to go. Now, using the triangular inequality, or otherwise, show that the modulus z is less than or equal to the square root of 5 plus 1. So I drew myself up a little picture. It doesn't have to be to scale or anything. I'm just saying, oh, here is some vector which is OZ. And somewhere else there'd be a vector 4 on Z. Well, the third side of that triangle, I know I need a triangle. They've given me the hint, use the triangular inequality. There's the third side, and it happens to be that expression in the absolute value sign, because head minus tail, z minus 4 on z. Okay, but the triangular inequality tells me that any side in the triangle will be less than or equal to the sum of the other two sides. So I've said the modulus of z is less than or equal to the modulus of z minus 4 on z plus the modulus of 4 on z. But we know that this one is equal to 2. Let's turn it into a quadratic, because I know how to solve quadratics. And I get the modulus of z squared minus 2 times the modulus of z minus 4 is less than or equal to 0. Well, I'll complete the square on that one. Modulus of z minus 1 squared is less than or equal to 5. That's feeling nice. I've got the number 5. Number 5's in my answer, so I feel like I'm on the right track. Take the square root of both sides, and I have that our modulus of z is in between these two values. So it's certainly true that it is less than or equal to the square root of 5 plus 1. Also that year, this was in the final question, because remember there's 16 questions in the Extension 2 paper, was this. Now they've given us a square in our Argand diagram, and they've given us the 4 vertices. But we have these other ones. ZA, and they've told us that's 5 plus I. Okay. They haven't told us about B and C. They just lie on these ones. But it does create an equilateral triangle. Find the exact value of B. We want to know what B is. Okay, that's what I want to find. I actually do have some information about it, because notice it's on the horizontal vector side, whatever you want to call it, but notice the imaginary part is the same. Therefore, I do know the imaginary part of B. I can get that straight away. I don't know the real part, so I'll just call it B. And similarly with C. It's on the horizontal line where the imaginary part is minus 5i. So I can give that coordinates as well. Let's name some of these vectors. BA, the one joining B and A, I'm just calling it the vector U. That would be head minus tail, B minus 5 plus 4i. And I'll also join up C and A. There's my expression there, C minus 5 minus 6i. But what I know is to go from one to the other, I'm rotating, well, it's an equilateral triangle, 60 degrees, or pi on 3 radians. So I do know that to get the vector v, I could rotate the vector u pi on 3 radians, or multiply by cos pi on 3 plus I sine pi on 3. Ooh, let's expand that out. I've got an equation. I can equate real and imaginary parts, and then I could get a value for b and c. But the interesting thing about this one, let's expand the whole thing out. There it is. I really don't need the real part, because actually C I'm not interested in. Remember, they asked me to find B. I'm really actually only interested in B. So if I just look at the imaginary parts, there is no mention of C in the imaginary parts. I can get B from that. I get that minus 6 is the same as root 3 on 2 B minus 5. I'll play around with that, make B the subject. You could imagine that particular year, they would have come up with this answer and they're probably going to think, I've done something wrong, it's horrible. You're expecting some nice neat number, but it's not always going to be a nice neat number. That's what B is. 5 minus 16 on root 3. I didn't bother rationalising the denominator because look, 3 doesn't go into 16, it's not going to cancel anyway, so I'm happy to leave it like that. But I now have B, because that's what I was looking for. I was looking for the real part. We already knew the imaginary part. So there it is. 5 minus 16 on root 3 plus 5i. Okay. So 1e